Hello.
Good afternoon, Dr. Francis.
Good afternoon. How are you?
I'm fine, thank you.
How's work? How's family? Everything going?
I'm fine.
Good.
Fine. Mhm.
Where's everybody now?
Let me go and close it.
Good afternoon, sir.
Hello. Good afternoon.
Hello, sir.
How's everything going?
Hi, sir.
Where are your people now?
To the lead on the way.
No, it seems if this machine learning is stressing us, then maybe we'll leave it now. Abby?
Am I supposed to I feel like I feel like it would make sense if there was a way to balance it, such that those that want to go, because machine learning and Python feel like something is like a black hole. The more you go, the more things you see, the more things you see you need to see. So I feel like maybe there's a way we should balance it or something. I beg, I don't know. I don't know, sir. I don't know. I don't know. I just wait small. People will join in.
Consultant IJ, good afternoon.
Hey, Madam Vivian. Good afternoon, ma.
Yeah.
Hallelujah.
But my own Can we start? Others will join.
Consultant IJ, you push that too. I'm here for moral support. I am lost.
Yeah, I think that's the challenge because if you come halfway, when you don't follow from the beginning, especially on this area, to be looking, let me just rest now. But Vivian, did you join us last week?
Yeah?
I said, did you join us last week?
No. I was not around. Yeah.
So let's just have, I think we can just start and let's see how we proceed.
Okay. Because right now, I don't want to go into the core coding now because the way you code it, they are all similar. They get in terms of the machine learning algorithms to use. Okay. But the challenge I have noticed is that most of you don't know when to use what. Okay. So last week we started with linear regression, isn't it? At least, do we know when to use linear regression now?
Yes, sir.
Yes, sir.
Okay. So when is it more appropriate to use linear regression?
We have continuous variable for the target.
Yes, when you have linear continuous variables, okay. So if you have y as a function of x, isn't it? And this y can be things like prices, isn't it? They can take any value because one of the assumptions of OLS is to what? That this your dependent variable is random. Do you get? Is random. You can take any value. So it can be what? Continuous. Any value. Okay, good. But sometimes, so what we are going into today is classification. And I also showed you the challenge of linear regression when you are using your linear regression. This is the problem of overfitting. Either you are using what? The lasso regression or what? The ridge regression. I think we talked about this last week, right? These ones are just other algorithms to overcome the problem of overfitting. Okay. You know when a model is overfitted?
Yes.
When is a model overfitted?
I think it's when there are too many more variables, too many variables, unnecessary variables.
I think it's when you use it again, you understand it and it's giving you almost the same response. So the accuracy.
When you use the train, isn't it, Peter?
Yes.
It performs very high, isn't it?
Yes.
But when you run the test data,
okay,
it now performs very low or poor.
Oh.
Underfitting, you use train, is poor. You use test, is poor. So that's why you now have to, that's why they tell you need to add more data sets or get more features. Okay. Because once you understand this one, it is the foundation of every other thing you are doing. So that's why I took time to explain even the mathematics behind it, the algorithm. When you hear the algorithm, at least you have seen the algorithm now, manually now, isn't it?
Yes, sir.
All right, so today we are going into classification. Okay. Now remember, just like your linear regression, okay, where you have y as a function of x. But you see, in terms of classification, okay, that means this your target variable can take only either two possible outcomes, right? Or the target variable is limited. Remember the assumption of the linear regression that this value here is what? Is random, isn't it? In regression, that your target variable is random. Is that not it?
Yes.
But you see some situation where what you are trying to predict, this value is limited. For example, yes, no. true, false, isn't it? Which other one? What other way can we classify it? Yes, what other way can we classify it?
Something claim or not claim.
Eh?
Claim or not claim for insurance.
Claim or not claim, isn't it? Insurance, fraud or not fraud. Can you see that? So it means that this your target variable has become what? Limited. Right? It has become what? Limited. So which means if it's limited to only two possible outcomes, for example, true or false. Okay, so if it's true, we assign 1. If it's false, we assign what? 0. Can you see that? Or sometimes you can have more than 1. It can be 1, 2, 3. Right? For example, which party is this person likely to belong? Isn't it? Then you now say, oh, it is APC. It is PDP. It is Labour, isn't it? But you see, in this case now, this one is clear, isn't it? True or false. What you are trying to actually predict, is this true? Right? But in this case, they are not of this. Can we say APC is better than PDP, PDP better than Labour? Can we say that?
No.
So they are all on the same scale, isn't it?
Yes.
And if you remember your measurement in statistics, isn't it? We call that what? What do we call it? When we look at measures, for example, male, female. Can we say male is better than female? But we assign numbers 1, 2. Do we say male is better than female?
No.
No.
So in that case, what kind of measure is this?
It's called nominal.
It's called nominal. Good. It's called nominal. Good. Okay. Now, for example, if I tell you, choose your preference, isn't it? Maybe different network, MTN, Airtel, isn't it? Glo, 9 Mobile, and I say choose your preference. Choose your preference, isn't it? So if I write, for example, on a scale of 1 to 4, okay, rank them on a scale of 1 to 4, isn't it? 4 being the most preferred, 1 being the least preferred. So I now write 4, I write 3, I write 2, I write 1. So in this case now, is 4 greater than 3?
Yes.
Is 3 greater than 2?
No.
Yes.
Okay.
And just for ranking.
Yes, now when you are ranking now, ranking is just different from assigning.
Okay.
You are ranking based on your preference, isn't it?
Yes.
If you are ranking based on your preference, it means that if I give Airtel 4, it means I prefer Airtel to 9 Mobile, isn't it? If I rank these 3, it means I prefer 9 Mobile to Glo, and here I prefer Glo to what? MTN. Can you see that? So what kind of measure is this? What kind of measure is this? We have nominal, isn't it? So we're talking about measurement. We have nominal. What kind of measure is this one? You know, here it's just like it's just like me giving you this thing. Say, I like. Okay, let's say for example, I like Peter Obi, isn't it? You make a statement. Strongly agree, undecided, decided, strongly agree, and now assign it 5, 4, 3, 2, 1, isn't it? Now, is 5 greater than 4 in this case? Is 5 greater than 4?
Yes.
Is 4 greater than 3?
Yes.
Is 3 greater than 2?
Yes.
So that tells you what? What kind of measure is this?
It's an order.
Order. This is order. This is order. Or what they call ordinal measure. Ordinal measure. This one is called what? Nominal measure. Is that clear? Is this clear?
Yes, sir.
Nominal and ordinal measure. Okay, good. So that is why when you look at your target variable, that variable is limited, isn't it? It is what? Limited. So we'll take the first one, it's limited. Maybe it's limited to only 2 possible outcomes. Can you see that? Only 2 possible outcomes. We call that what? Binary. It's called what? Binary. Now, if you run normal regression on this your binary, it's not that you don't get result, but that result will be what? Misleading. Okay, which means if it's only limited between 1 and 0, it has now moved from what you call your least square method to what they call maximum likelihood. It's called what? Maximum likelihood. So anything here, likelihood, what does likelihood mean? What does likelihood mean? When you hear likelihood, what does it mean?
It can happen.
Likelihood. When you hear likelihood, what does likelihood mean?
Possibility of happening.
It's probability now. Yeah, it's probability. So it has moved from your normal least square, from that continuous to what? A probability. The chance of it happening between what? 1 and 0. Is that not what we say probability? That the probability of an event occurring must lie between what? It lies between what? 0 and 1. Okay, and look at this. In your normal regression, this is what we are trying to do. You have all your points here, isn't it? You have all your points here. Your objective is to what? Get a line of best fit, isn't it? To get a line of best fit. But in this case now, we have only 2 possible outcomes. We have a 0, and let's say we have a 1, isn't it? So it means that the values can either lie like this, on this line, or it can lie on this line. Can you see that? Can you see that? So now the methodology you are using cannot be the same again. Okay, the methodology you are using cannot be the same again. So that's why when you are talking about your logistic regression, isn't it? Your logistic, we are simply saying that where your target variable has only 2 possible outcomes, isn't it? 1 and 0. 1 is true, possibility of it happening. False. Remember our Titanic. What was our objective there in Titanic?
Survival.
To predict whether it survived or not survived. Did the person survive? True. Otherwise false, isn't it? So where the person survived, we assign 1, the otherwise 0. Is that not it? So the kind of regression you run there is called what? Binary logistic. It's called what? Binary logistic what? Regression. Did you get that?
Yes,
So
sir.
that is why in your normal regression, you have been a line here, but this one is S-shaped. Can you see that? For your logistic regression, it is what? S-shaped. Which means you cannot just use your normal line of best fits. So actually, what you are actually doing there is to find like a, I don't want to go too mathematical. But what you have, this S shape is called a sigmoid. It's called a sigmoid function. Sigmoid function. That's what they call that mathematically. Okay, and it's usually given as 1 all over 1 plus e raised to power t. You know, this is your, what do you call that? Euler's number. What is that Euler's number? Is that 2.1? Is it 17 or 718? Okay, so this is usually the function that you run. So at the back end of that logistic you are running, this is what is happening there. Just like your normal regression, which is your y equals to a plus bx, isn't it? And you get your value of a, get your value of b. That's exactly what is happening here. Because your logistic regression is also linear. It's also what? Linear. Okay? But it gets linear up to this point and up to what? This point. So that's why you are looking for the probability that is going to happen within this one and this value. So hence the name maximum likelihood what technique. It has a limit, upper limit, that has what? A lower what limit. So anything about classification, we are talking about what? The use of what? Probabilities. The likelihood it will happen between what? The minimum value and what? The maximum value. So where your target variable has only two possible outcomes, 1 and 0, it is called what? Binary logistic regression. Do you get that? It's called binary logistic regression. Is that clear? So for example, some use cases. Is this email spam or not spam? Isn't it? If it's spam, what do we do? If it's spam, what do we do?
We send it to the spam folder.
Yes, it's spam folder. So if you are now trying to measure it mathematically, how do you do it? If it's spam, what do you do?
Assign 1 to it.
You assign 1, isn't it? You assign 1. Otherwise, you assign what? 0.
0.
Isn't it? Will a customer buy a life insurance? Isn't it? If he's buying life insurance, what do we do? You assign 1, otherwise assign what? 0. Right? I think that is clear now. Will this person survive or not survive? If the person will survive, what do we do? Assign 1, otherwise assign what? 0. Is that clear? So when do we use logistic regression now? So when do we use logistic regression?
When it's a binary problem of 1 or 0s, when we need probability.
Yeah, so as long as the target variable, this target variable is limited, isn't it? Is what? Limited. So it can either be binary, it can either be nominal, is it not? Nominal, or it can be either be ordinal. Okay, so this nominal, so let me just explain the different types of regression. So in terms of the type of logistic regression that you can have, we said if it has only two possible outcomes, it is what? Binary what? It's called what? Binary logistic regression, isn't it? But where that y, is it not? So our focus is on this y, isn't it? Where it has only two possible outcomes, 1 and what? 0. Isn't it? So we use what? Binary logistic what? Regression. Okay. But where this y, the measure of this y is nominal, isn't it? You understand what is nominal? It's nominal, so it can be 1, 2, 3. But it doesn't mean that 1 is better than 2 or 2 is better than 3. Or 3 is greater than 2 or 2 is greater than 1. In that case, since it is more than 1, we call it what? Multinomial. It's called what? Multinomial. And this happens especially when you have more than one word, especially for your multi-regression. But in this case, the way you measure it, it has more than one word measure. So it's not just 1, 2. If it's just 1, 2, it's just, you can just say it's nominal. But 1, 2, 3, 4, 5, we call that what? Multinomial. Okay, so this is called the what? So the kind of regression you run is called multinomial logistic regression. Exactly. But where this y, this value of y has an order, for example, 3, 2, 1, and 3 is greater than 2, 2 is greater than 1. So there's order, isn't it? So it is called what? Ordinal. It's called what? Ordinal logistic regression. I know if you have been studying, this is the only one you have. I'm sure this is the only one you have been familiar with. Is that it?
Yes.
Okay. So just understand that. How do I know which one to use? Once it's a classification, right? Classification case, it means that my y, I will classify it, isn't it? But how I classify it depends on how I'm going to measure it. If it has only 2 possible outcomes, it is what? Binary. So if it is binary, which means only 2 possible outcomes, true or false, that means I will either assign 1 or 0, isn't it? 1 for true and 0 for false. Okay. So in that case, what kind of regression do we use?
Logistic.
Binary logistic regression. It's what? A binary logistic regression. Okay. But if this target variable, isn't it, has maybe like 3 or more categorical variables or 3 or more categories. 3 or more categories, isn't it? For example, you can assign 1, 2, 3, 4. And there is no order. You see the difference now is that there is no order. Isn't it? What kind of regression is that? And there is no order. What kind of regression is that?
Okay.
It's called what? Multinomial logistic regression. Okay. But where we assign it and it has from 3 and above, isn't it? Where the target variable has 3 or more categories or outcomes with an order. What kind of regression is that?
Ordinal.
Ordinal logistic regression. Can we see that? Is that clear? Is that clear?
Yes, sir.
So now it is clear how to know when to use regression, isn't it?
Yes.
When to use binary logistic, multinomial logistic, ordinal logistic. Because the same way we have been running those codes, it's the same way we are going to do it for all of them. Okay, but the only challenge is that you may not know when to use what. So that's why I'm just trying to explain each of them one by one. So we see under classification, we have looked at one of them now, which is what? Your logistic. But under logistic, we have these 3. 1, 2, 3. But most times, this is the one you see. Isn't it? But it can be also, these ones can also be part of it. Are we okay with logistic regression now?
Yes, sir.
Clear?
Yes, yes, sir.
All right, good. So let's look at another one. Let's look at naive Bayes. Naive Bayes, isn't it? We said this naive Bayes comes from where?
Bayes
it comes
theorem.
from your word Bayes theorem. From Bayes theorem, isn't it? And when do we use Bayes theorem?
I think we're trying to get the probability of the conditional probabilities, like
yes, actually,
when you have the likelihood of an occurrence, or when you're trying to ascertain the conditional probability of an event based on the occurrence of another.
Yes, but when you have new information, isn't it? Then you now have to now revise that probability, isn't it? So it's like having what? The revised, or what they call the posterior probability, based on what? New information. Okay, so we know probability of an event is that probability of A occurring given that B has occurred, isn't it? Means that probability of B has already occurred. This event B has already occurred, isn't it? Is that not how it's done?
yes.
Then we now have what? The conditional probability, isn't it? Of B given A times what? Probability of what? A. Okay, so what are we trying to do? We are trying to find what? The new probability, isn't it, of A, given the new information, given that this has already what? Happened. Okay, so it's usually like saying a revised probability for more than one event. So that is what this Bayes part is doing. That's the Bayes theory. But you see, naive. When you say somebody is naive, what does it mean? When you say somebody is naive,
Like he doesn't know anything.
he doesn't know anything, isn't it? So naive Bayes is making a naive assumption that these events are independent. Can you see that? That these events are what? Independent. But remember, this conditional probability is that one depends on the other. Do you see that? Your Bayes theorem says that what? Probability of A will occur given that what? Another event has already occurred. Is it not? Can you see that they are dependent? Do you see that they are dependent? So naive Bayes is now saying that it's making what? An assumption that these events are what? Independent. So that's the naive assumption. Hence the name naive Bayes. Is that clear? Is that clear?
Yes, sir.
Yeah. So is that based on that assumption? We call it what? The naive Bayes. But actually, what is just simply trying to do is just to what? Help you to what? Classify that your target variable y, isn't it? Will happen. Okay? Will happen. Given that these other events or these other features are independent. Okay? So that's why when you are dealing with your naive Bayes theory, it's just like say let me see a typical example that we can use. It's just like say you know how you normally calculate your probability, right? If you see, for example, let's say we have event. Let's say we have fruits, different fruits. Let's say we have what? Let's say we have apple. What other fruits can we have there? Let's say we have banana, right? Let's say we have, what other fruits can we have? Okay, let's say other fruits. Let's say other fruits. Okay. Now let's look at it now. Let's say the colors, right? Maybe this one is yellow. Okay. Let's say this one is the size is big, right? It's big. And let's say the taste is sweet. So we have three different features. We have color, we have size. You know, we have color, we have size, we have what? Taste, isn't it? So based on this feature, we want to now predict if it is what? Apple, if it is banana, or if it's what? Other fruits. Can you see that? Can you see that? So whenever you create it like this, you know, this is your this is what you refer to as your, is it your, what do you call it? Your contingency table or frequency table. Let's say, for example, this your sample, you took 175 apples, isn't it? That are yellow. We have 200 bananas that are yellow, isn't it? And we have what? Maybe 25 other fruits that are also yellow. When we add them up, what would that give us? What would that give us? What will it give us? That will
400.
be about 400. 400. In terms of the size, we have what? Let's say we have 225. Let's say we have 150. Let's say we have 50. If we add up here, what do we have?
Still 400.
Is it 400? So this is.
So that's for the apple.
This is 200. 200 plus 225.
Okay, for big.
That should be 425. Yes. For big, yes. Then let's say, for example, for taste, based on this sweetness, isn't it? Maybe this one this one was sweet. Let's say this one we counted 175. Let's say this one we counted 25. This plus this will give us about 200.
200.
Now, if we are looking at in terms of apple, the total for here, what will be the total here? This should be about 400. This should be what? This 350 plus 175. That will be about what? Is that 525? Then here will give us about what now? That's 100. Is that 100? Then if we add up here, what do we have? 1025, isn't it? So you see, for example, this is what they refer to as your frequency table or contingency table. Okay. So basically, when you are doing your probabilities now, if you say what's the probability that the apple is yellow, what would it be the probability?
To be 175 over 1025.
That the apple is yellow.
That the apple is yellow. 175 over all apples. That's 400.
And is yellow. What is probably that the apple is yellow?
Okay, probability that it is first an apple. 400. Then that the apple is yellow. Voila.
No, 175.
Is what it's going to be what? It's going to be what? That the apple is yellow. Probability that the apple is yellow. So that is yellow. How many is yellow?
175.
That is yellow. Look at the total. This is yellow now. What is total for yellow?
400.
400 now. So it's going to be what? 400. And it's apple. What is it going to be?
175.
175. So if I do this now, so 175 over 400, what would that be? So what would that be? 175 divided by 400, what would that be? What is that going to be?
0.43. 0.43.
0. Point what?
4375. That's 0.44 approximately.
Okay, approximately 0.44, isn't it? So how do we interpret this now? That means there's what? Out of 100, if you take out of 100 yellow fruits, isn't it? It's saying that 44 of them will be what? Apples.
Apple.
Can you see that? So, and this is how you basically calculate your probabilities. It's just to do a bunch of counts, isn't it? And just find what? A ratio. So that naive Bayes just making an assumption that all these features are what? Independent of each other. So at the end of the day, it's just going to do a simple what? Count like this. Just do a simple count for you and calculate a probability for you. So if it is great up to, if it's going towards 1 or less than, so if it's, let's say 0.5 now, 0.5, if it's greater than 0.5, it's tending towards 1, isn't it? If it's less than 0.5, it's tending towards 0. Is that not it? So if he does this calculation now, is it greater than 0.5? Is it greater than 0.5?
No.
So it is going towards what?
0.
0, isn't it? So it will tell you that this is not apple. Can you see that now? But if it's above 0.5, is that going towards tending towards 1? Is it tending towards 1?
If it's
0.
above, yes.
Yeah, if it's above, it's classified as if it's going towards 1. So we say this is what? Apple. Can you see that? So that is what naive Bayes is doing for you. So once he does the calculation for you like this, once he gets it, if this value is greater than 0.5, it will assume that it's what? Likely going to be what? 1. If it's less than, it's likely going to be what? 0. So this is your true and this is your what? False. So it is based on this, you do not classify it, whether it is apple or not what? Apple. Do you understand that? So that is how naive Bayes is doing this classification. So it's just like if you just calculate probability of each class, then pick one, which one is the highest probability, is it? Then classify it. If it's going towards, if it's greater than 0.5, we say it's going towards that one. Is that clear? Is this clear?
Yes, sir.
So that is what naive Bayes do. Okay, so that's what naive Bayes do. Sometimes they'll just say this, the model is too simple, right? But sometimes some features the thing performs very well. Okay, so you just have to watch. That's why you see when you are doing your different classification models, isn't it? You just have to what, take the one which has the highest what accuracy, and if you bring in new data, does it perform well? Okay, so that's exactly what your naive Bayes is doing for you. Are we okay with that? Are we okay with naive Bayes now?
Yes.
All right. So another common one you hear is KNN. Have you heard of KNN? K nearest neighbor. K nearest neighbor. Neighbor. So you hear KNN, isn't it? It's also what, a classification. Eh? But although sometimes they will tell you that this one is also a very lazy algorithm. Okay. So remember again, what you are also using it for is for classification. Okay, we have seen one, we have seen logistic regression, isn't it? We have seen another one, naive Bayes method, isn't it? So another one now is what, KNN, because these are some of the common algorithms you are going to see. Okay, so KNN, what KNN is simply doing, like for example, let's say we have two distinct, let's say we have A and B, right? We have A and B. So maybe we have different groups. We have another group here. We have another group here, another group here, another group here, another group here, another group here. Now, if we now bring a new data set, and that, let me put on here, and that data set is here. We have a new data set now, isn't it? And that data set is here. Now, which group does it belong to? Let's say this is A and this is B. Which group does it belong to? If you have it, this point here, which group does it belong to, A or B? Which group does it belong to, A or B?
It will be the one that is closest, like.
So which one is closest now? Is it closest to A or closest to B?
I'll go with B.
You will go with B, isn't it?
Yes.
And that's exactly what K nearest neighbor is. So it's a classification, isn't it? So it will go through the data and say, okay, based on this, if you calculate the distance between this and this, calculate distance between this and this, calculate distance between this and this, calculate distance between this and this, isn't it? So it is based on the one that is closest. It will now tell you, okay, based on what I am seeing here, I am going to classify it as what category, what, B. You get that? So KNN just simply tries to what, predict the correct class for the test data. So if I have a new data, it will classify it either what, A or what, B. By doing what? By calculating what, the distance. Okay, between what, the points, either this class and what, this class. Because the first thing you need to first of all do is that you will need to select the value of K. When you say value of K, so how many groups? In this case, we have taken 1, we have taken 2, we have taken 3, we have taken 4, isn't it? Now, sometimes why is it just to use this 4 like this? It is better to use an odd number. For example, it will be better for us to use 3 or 5. Okay, so that just in case you will not have that problem of time. So that's why most time when you are picking your value of K in terms of the number of parameters that are close to it, it is better to use what? An odd number. Because if I go and pick 4 now, if I go and pick 4, 4 means that at the end of the day, maybe 50-50, isn't it? So we don't want that case. We want to classify it either this or this. So that's why most time you use what? An odd number. So for example, you can take this one and take this as what? K is equals to what? 3. So do you understand what has happened there? So once we have done that, once we have taken that, so either we take 3, 5, 7, isn't it? 9. Okay, so just like that, we can take value. The value of k can be any of them. Okay, so I can take any 3, any 5, any 7, any 9. But that value of k, that's the number of group you are picking from here. Either I take 2 from here, 1 from here, or maybe I can take 5, 1, 2, 3, and another 2 from here. Okay, so you pick the values. So once you have done that, the next thing you need to do is to calculate what? The distance. Okay, and that distance, they call it, I think Euclidean, they call it Euclidean distance. They call it Euclidean distance. That's what they call it, Euclidean what? Distance. Okay, and what you simply do is simply measuring the space between A and what? B, which means if I have 2 values, it will first of all take maybe like say x1 minus x2. Okay, so that's for first group. Then you could square it, plus if you take from the other group, y2 minus what? y1, and also what? Square it. Whatever answer you have, whichever is closer, okay, whichever is what? Closer, it will now what? Assign it as that group. So that is what they call Euclidean what? Distance. But you have other ones like what they call Manhattan distance. But this is another common one they use. Okay, so KNN simply, what does KNN do? It just looks at the 2 groups. You will assign random. So either you take any 4, any 5, any 3, any 7, just take any odd number. Okay, it will calculate all the distance. Whichever is closer, it will assign it to that class. So if it's closer to B, it will assign it to B. If it's closer to A, it will assign it to A. So that's what it's just doing there. Is that okay? Is that okay?
Yes, sir.
Yes.
I'm just wondering what type of data we'll use KNN to analyze. Because
okay, what kind of data? Now,
yes.
It's the same categorical data now. The same categorical data. Okay, so as long as the data is categorical, it's just like grouping. Somebody is in APC, somebody is in PDP, somebody is in another party, isn't it? Or if you want to make it easy for yourself, just has 2 possible outcomes. Okay, so it's either going to be this group or this group. I think that will be easier in that case. Anything you use logistic regression for, you can also use KNN. Same thing with your naive Bayes. Okay, but naive Bayes can also be multinomial. So just understand, as long as the group can either be what? It's categorical, which means it can either be binary, nominal, multinomial, or what? Ordinal. You can apply any of these algorithms. Is that okay?
Yes, sir.
All right. Now, another one again you hear is, which other common one again you hear? Support vector here, SVM, that's another common one. Support. Now, but take note, you see for this KNN, there's nothing like these 2 here, naive Bayes and KNN. At the back end, there's no algorithm like you have in your, there's no core algorithm like you have in your, what they call it now, in your regression and logistic regression. So that's why sometimes they refer to them as what? A lazy algorithm. Okay, they just look at pattern, whichever is closer or looks like it, they will just assign it there. But you see, when you are running or choosing this method, isn't it? If you don't understand what it's doing, you just see result, but you don't understand what is happening at the back end. Okay. And again, take note, all of them are all what? Linear models for classification problem. They are all what? Linear models for what? Classification what? Problem. Is that okay?
Yes.
Okay, so let's look at another one again. Now, this SVM, yes, just support vector machine. Yes, SVM stands for what? Support vector what machine. Okay. What it simply does is that just like we have that our, what do you call it now? This our k nearest neighbor. Yeah. So let's say we have two groups. Let's say we have one group here, one group here, one group here. So let's say all this one is A. We have another group here. Let's say we have another group here. We have another group here. Okay. You know what it's trying to do? What it's still doing is that it will first of all put a line here to demarcate it. Put another line here to demarcate it, isn't it? So if a new data comes, isn't it? Once a new data comes now, what is it trying to do? It's now trying to calculate what? The distance. Because you will see there are some that will stop on this line here. Okay, some will stop on this line. Okay, that's where to capture all the ones that you can capture on this line. All the ones you can capture on this line, you capture it just like your normal regression, isn't it? But it will not demarcate it. Okay. Now, every item that is on this line is what is referred to as what? The support vector. It's called what? The support vector. Okay. And what it's going to do is going to put a line in between to divide them into two equal parts, which is called what? It's called what? A hyperplane. It's called what? A hyperplane. So every point on that line is called what? The support what? Vector. So it's going to calculate the distance from this line to this line. This can be positive, isn't it? It can calculate from this line to this line, which can be what? Negative. Okay. By the time you what? Sum up all of them. By the time you sum them up, because this from this point to this point, from this point to this point now, they refer to that as the maximum or maximized margin. It's your margin, isn't it? It's your margin, but this is the maximum margin. It's the maximum. This is the highest point it can be. So any point within there is just trying to calculate what? The distance. Whichever is closer, okay, whichever is closer, it will now what? Classify it. So if I have any data here and I calculate, if it's more closer to this point or closer to this point, it will now classify it either on this group A or classify it towards another group P. So it's almost like your this thing too. It's almost like this one. This is your K nearest neighbor. But the only difference now is that it's now using what? These lines, the hyperplane to now do it. So it will be adjusting them to adjust the line this way, it will calculate the distance. It will adjust the line this way, it will calculate the distance until it gets what? The best. Okay. So once it can what? Get the best or the one that is closest to any of them, then we now call that what? It now was simply what? Classify it as either what? Group A or what? Group B. So that is what it just tries to do for you. So it just what? Creates the distance, calculate the distance for you. Whichever is closer to which, it will classify it either to group category A or what? Category B. So that is what they refer to as what? The SVM. So you see, at the end of the day, all they are trying to do is to what? Do what? Classification. Okay? They try to do what? A classification. But another point again is that this SVM, most times when you use it is when the data set is not so large. Okay? When the data set is not so large, you can also use what? It's more appropriate for when the data is small data. Okay, it's more appropriate for what? Smaller what? Data. Okay. Then you have another group again. Are we okay with SVM? Are we okay with SVM?
Yes, sir.
It's just like
Yes,
it's just almost like your KNN, but the only difference is that it uses planes and hyperplanes. Then you start measuring the lines, and taking the distance. The one that is smaller, then you not take it and classify it either as this one or this one. So it's under what? Classification. So remember, under classification, We have seen what? Logistic, isn't it? We have seen what? We have seen logistic. Which one do we see again?
KNN.
Naive Bay, yes. We have seen naive Bay. We have seen what? KNN, isn't it? Now we have seen what? SVM. You see the reason why that's no free lunch theorem. You see that? You see, it says that what? There's no one theorem that can, or one algorithm that have the answer to everything. So that is why you try as many as possible and take the one that has what? The highest what? Accuracy. So another one again we'll be looking at is called decision tree. It's called what? Decision what tree? Decision tree. Decision tree. Now you know your decision tree, right? Your decision tree is just like a graphical representation, is not of a sequential order. So if this happens, is it not? If this happens, for example, you say, "Are you hungry? Are you hungry?" Isn't it? It's either yes or no. Is it not? It's either yes or no, right? If it's yes, if you are hungry, then what do you do? If you are hungry, what do you now do?
Look for food or not?
You look for food. But you see, before you look for food, now you ask yourself, do I have money to eat? Isn't it? So if I say I have money, isn't it? So I have, let's say I have maybe, let's say $10 to eat. So I say I have $10 to eat. Then if the answer is yes, then I can go and what? So I have $10, so I have money to eat. Okay. If the answer is yes, so I can now say, okay, either I go and do this, or either I go to a restaurant, isn't it? Or if I don't have enough, if the answer is no, I can go to Buka and go to Mama Put, isn't it? And go and eat. But if I am not hungry, there's nothing I can do now. I'll just go and sleep. So what it's doing is that your decision tree, what does it do? It's just showing us a sequence of decisions that we are going to take, is it not? With their corresponding what? Output. Okay. So once this happens, these are the possible what? Outcomes. Once this happens, these are the possible what? Outcomes. So it puts it in a tree form. But you see, when you have a tree like, when you have a decision tree like this, sometimes when you have to combine other trees to eat, you know that saying, what's that saying, that a tree does not make a forest?
Yes.
Is that not it?
Yes.
A collection of trees makes a what? Forest.
Yes.
So a collection of decision tree gives rise to what they call random forests. So that's what gave rise to the other algorithm called random forest. Have you heard of random forest algorithm?
So you mentioned it.
I've mentioned it. Okay. So a collection of decision tree gives rise to what? Random forest. Okay. So you see, your decisions are based on what? Conditions, isn't it? So it either is happening or not happening, happening or not happening. So it is based on this, it will now classify all those your features and say, oh, if this happens, this happens, this happens, it's likely that this is going to what? Happen. Okay. But the challenge that you have with your decision tree, most time, if the decision tree is just one like this, usually it's small, isn't it? It leads to what they call what? Overfitting. To avoid this problem of overfitting, you now need to bring in what? Other trees, which leads to what? Our random what? Forests. So random forest is just a way to what? Overcome what? Your decision tree. Just like your regression. That's your lasso regression and ridge regression help you to overcome the problem of what? Overfitting in your linear regression. That is exactly what your random forest is. So random forest simply what? Builds multiple what? Decision trees. So it's just like saying I can have one like this, can have one outcome like this. This outcome can have another outcome. This outcome can have another outcome. Another outcome can have another what? Set of outcomes again. Can you see that? So these outcomes, so they just become one, because each of them, they are called nodes. They are called nodes. But the last ones are called the leaf. The last one, you know, in the tree now, the last ones are called what? A leaf. They are called what? The leaf. Okay, so you can have as what? Many as what? Possible. Okay, but the point is just saying is that it is trying to what? Avoid this problem of what? Overfitting. Okay, so by combining other decision tree, what is doing is called, that process is known as what? Bagging. The process is known as what? Bagging. So when you collect what? Different what? Trees, what it's simply doing is learning from this tree. It will learn from this tree, learn from this tree, learn from this tree, learn from this tree, and take all the best features. And take all the what? Best what? Features. Okay, and that's why you see that when you are dealing with your random forest there are basically two concepts you must understand. Okay, two concepts you must understand. This bagging comes from a concept called assembly. It's come from a concept called what? Assembly. You know when you say you're assembling something, right? When you say we're assembling, when you say assembly, what does assembly mean?
Like you're gathering stuff.
You are gathering, isn't it? So when you are gathering different things, isn't it? When you are gathering different things or combining different models, so when you are combining different models, they call it what? Assembly. Just like assembly parts, different parts, isn't it? That will now fit together. But in modeling, we call it what? Assembly. So assembly simply means what? You are learning from the different what? Combining the different what? Models. So this assembly, there are two parts of this assembly. You have what they call bagging. You have bagging and you have what they call boosting. You have bagging and you have what they call what? Boosting. Okay. So random forest, this your random forest uses the method called what? Bagging. Okay. So when you say bagging, bagging simply means like resampling. It's more like what? You are just resampling. You are just taking different what samples. You know, I will take from here with a different sample, take from here with a different sample, take from here a different sample, take from here a different sample, and come up with his own what model to what predicts. Okay. But this boosting part deals with more of what? Reweighting, like in terms of your features. This one looks at resampling the data size, the sample size. But this one is talking more about what? The feature selection. The number of features that you can have. Because with more features you add, isn't it? The more features you add, the different the predictive power of the model. So what it's going to do, it will take one of them, is it not? Get the coefficient, isn't it? Based on the number of trees you have taken, if you start what, like taking like an average of each of them. So the coefficients that come out there will be what? A reweighted what? Coefficient. So when you're not predicting, it's not predicting based on what? The sample size now. It's predicting based on what? The features. Okay, so it will learn based on all of them. And it's based on that. So most of the ones that uses this boosting method, you will hear of things like gradient boost. I'm sure we have heard of gradient boost. Gradient boost. Have you heard of gradient boost? Extreme gradient boost.
No, sir.
Okay, you have another one, light gradient boost. You see, these are now different kind of boost. There's another called adaptive boost. So they call it adapt boost. Okay, so these are now the methods used in what? Either decision tree or your random what? Forest. And all of them are all about what? Classification. They are all about what? Classification. Because remember, when we talk about you are building your model, when we say a model, what does a model comprise of? When you say you are building a model, what does it comprise of?
Features.
Data and algorithm.
The what?
Data and algorithm.
Exactly. It's looking at what? The data and the what? Algorithm. Bagging deals with the data part. Isn't it? It deals with actually resampling of that data. But boosting deals with what? the algorithm itself. Okay, you just look for what? The algorithm and what? And again, take note, they are all what? Linear also. They are all what? Linear. Okay, so these are the different kind of what methods you are going to be what seeing. Okay, these are different methods you are going to be what seeing. Then, although we are not, when we come back again, we'll start dealing with what they call it now, unsupervised learning. But these are the common features you are going to see for your what classification. Okay, so what we have seen so far is that, remember, under your machine learning model, it can either be what? Supervised machine learning, or what? Unsupervised machine learning, isn't it? So under supervised machine learning, we have looked at two parts. What are they? There's the regression problem, isn't it? And we have what? The classification problem, isn't it? Under regression problem, what have we looked at? Under the regression problem, what have we looked at?
Linear regression.
We have looked at linear regression. What have we looked at again? You have the lasso regression, and we have what? The ridge regression. Because these two help you overcome the problem of what? Overfitting. Isn't it? Because regression uses what? The y. Remember, y as a function of x. This value, this target, is what we determine the algorithm we are going to use. So where this is continuous, we are using what? The linear what regression. Okay. Remember, it can either be simple or multiple regression, depending on the features you have. But for classification problem, isn't it? Where this your value of y now becomes what? Limited. Where this your y as a function of x becomes what? Limited. It can either be what? Only two possible outcomes, which is called binary.
Binary.
It can be what? 3 or more without an order, which is called what? Multinomial. It can be what? 3 or more, but with an order called what? Ordinal. So based on that, we have what? Logistic what? Regression. And the logistic regression can be either what? Binary logistic regression, isn't it? Multinomial logistic regression, or what? Ordinal logistic regression. So that's for regression, logistic regression. For under classification, again, we can talk about what? Naive what? Bayes. When do we use this naive Bayes? When can we use naive Bayes?
We want to get the new probabilities.
Yes, it's especially for probabilities, isn't it? It's also classification with what? Probabilities, isn't it? So naive what? Bayes. It just groups them into like do a frequency for you and do what? The probability of it. So anyone that is closer, anyone that is greater than 0.5, it will classify it as what? 1. Anyone that is less than 0.5, classify it as what? 0. Okay. Then we look at what? KNN. How does KNN work?
The one that has the closest feature that resembles either one or the other side.
That's it, KNN. Yeah. Then we can also talk about what? Which other one again? SVM. When do we use SVM?
It's almost like KNN.
It's just almost like KNN, you know. But it just uses split to just divide it, and anyone closer to it to classify it. Okay. Then we'll talk about what? Decision tree, isn't it? Decision tree. Okay. Decision what? Tree. Okay. And random what? Forest. Because collection of what? Different trees gives us what? The random what? Forest. And under the random forest, we can talk about what? Gradient boost, isn't it? Extreme gradient boost, light gradient boost, adaptive gradient boost. So these are the algorithms you are going to see under what? Supervised machine learning. Is this clear now? Is this clear
Yes, sir.
now? Okay. Do we have any other data set that we can try? Which data set do we have that we can use?
Like a new one or one that we've worked on before.
Either a new one or any of them, so that we can try other algorithms and see how it works. Have we been trying any of those, what do you call it? Those challenges, machine learning challenges?
Yes, sir. Okay. I tried one with Olumide,
Okay.
one from Zind.
Okay.
It was something about financial inclusion, something. They said it was for beginners, so
Okay.
said to try that one. And it was, yes, so I have that data set. But otherwise, that one just showed us, it was almost similar to, it was almost exactly what we did, but that one they were saying whether the person is likely to have a bank account or not.
Okay, so if you are likely to have a bank account or not, isn't it?
Yes.
Okay, if you're likely to have a bank account or not. Okay. Okay. So in that case now, it's still like classification now, isn't it?
Yes, sir.
That is a typical case of what classification. Okay, so let's look at, let me see if we have any other data set we can use here. Okay, let me just open my Python listing. But the point is that you see, in any of those competition, isn't it? In any of those competition, or what we can do, let's, even before we start even all this coding, at least we already have an overview of what we are talking about now, isn't it? So in terms of implementation, right? In terms of implementation, right? So let's check. Let's look at cargo. Let's look at cargo, right? Let's go to cargo. So let me say cargo. So how you learn most of them, right? So how you learn most of them. So if I come here to cargo, right? If I come to, let me come to home. Script, okay, face image. All these ones now, you see all this face detection now. Even though they are still classification, you know that pictures are also numbers. You know this picture now, you are seen as a picture, but do you know they are numbers? Everybody's picture, yes, now pictures are made up of numbers.
So I don't think we can see your screen now. Or is it just me?
Oh, you can't see my screen?
Me, I can see. I can see screen.
Maybe it's my device.
Yes, I can see the pictures you are pointing to.
Exactly. All these are all pictures. You see, all of them have different shape, size of head, size of nose. They are all numbers. So when you are doing an algorithm, actually you are looking at as picture, but actually it's capturing numbers. Okay. So everybody's face will have his own unique number. So that's how I cannot classify you. Either you are male, you are female, you are young, you are old, because they all have different numbers. Okay. So when you come to your cargo, right, you just come, for example, search. Let's say, which one can we look at now? Okay, let's say, for example, let's see any other, okay, say competitions now. So these are different competitions. For example, Titanic, you already know what to do there, isn't it? House pricing, you already know what to do there. Let's even see house pricing. What have they done? Let's see which one they have done here. House pricing. So you see data. You see the data there, isn't it? You see the code. You see the person's code. So this is what this person submitted. So you can open that code. Where is the code now? Okay. Okay. Now I think there's one thing I'm not sure we have touched that scaling. I don't know that. Did we talk about scaling? To scale the data. I'm not sure we talked about scaling, right?
No, sir, we have not.
We didn't talk about scaling. Okay. Let's see. I just want to see the. But all these ones, you understand what they are doing here, isn't it? All this one, you understand what they are doing here? You know what they are doing in all these ones now, right? This is called EDA, exploratory data analysis. You are just doing your visualization, doing the descriptive statistics. They are called what? EDA, exploratory data analysis. Right? I'm sure everybody can do this now. Can we all do it? Can we upload chat in Python?
Yes, we can.
And that's basically what they are just doing there, isn't it? Don't mind the way their results are coming out. Just the Python, this guy is just bringing all of them. Okay. So I'm just checking that anything unique the person has done. I'm sure we can do this, right? Which chart is this?
Box plot.
What is it used for?
Look for outliers.
Outlier, exactly. That's like this person did not do any evil. I didn't see any algorithm there. The person did not run anything there. I'm looking for a typical one where the person will run everything and now test. Okay, let's try another one. Let's look for another one again. This is house pricing. So house pricing, if at all you want to use the algorithm, which algorithm is appropriate for it? Which algorithm is appropriate for it?
It's a continuous variable, so it will be linear.
It will be what? A linear what? Regression. It will be a linear regression. It will be a linear regression. This one submitted like 12 minutes ago. So can you see now? So this is what? Default prediction, isn't it? So once you have seen the default prediction, what kind of problem is it? Default prediction, what kind of problem is it? What kind of problem is it? Default prediction. Yes? What kind of problem is it? Default prediction, what kind of problem is it?
No.
Default, when you say somebody is defaulting, American Express, right? When you say somebody is defaulting.
Okay, whether he would default or whether he will not default.
Exactly, what kind of problem is that?
It's a classification problem.
The classification problem. It's a classification problem. What algorithm can you use?
Binary logistic regression.
Thank you, any of them. So that's what you start looking at. Okay, so the question now asks, what algorithm did this person use? Okay, you just check what the person has used. You see this one, like for example, this person connected to SQL, okay, to connect the data, especially where the data is very large. Okay. So I'm looking for the algorithm that the person has used. Did we talk about label encoding? This person no. That person not even do. Like this is not complete. This is not complete. Did we talk about label encoding? One hot encoding. One hot encoding. You will not do one hot encoding. Where you break the data into, for example, if it's male, female, you split it into male and female. You now be applied everywhere you see male, 1, otherwise 0. Anywhere you see female, 1, otherwise 0.
Yes, we did that, sir.
We did that.
So when we did that, it was map we used though.
Okay, we use map. We did not use one hot encoding, label encoding.
Abisa Moses, did we use label encoding?
No, we did not.
Map.
We use map.
We just use map. Okay, you know you can use map, you can use replace, you can also use that label and put it too. But the only difference is that one will now break them into many features for you. It will not break them into many features for you. XGBoost. XGBoost. So I'm just trying to see how anyone that I will see that they have used any of their listings. Number of components, okay. Features, XGBoost. Now, where is their accuracy here? Now, look at this one, right? This one is using a K-fold. That K-fold, which one uses K now? When it's trying to get the K, that is like KNN, isn't it? Where it picks the number. That's like KNN, right? But this one again, still using like your XGBoost. That one, XGBoost is under what? XGBoost is under what? XGBoost is under what? Look at the classification that we have done now. XGBoost, it falls under what? Ensemble. So let me see what this guy has done. Can you see this one score is 0.9, 0.799. Can you see they don't even get some don't even get to 90%. And that thing again you can also do, you can look at what they call the leaderboards. Can you see leaderboards? You can now check. So can you see the highest? 0.8. Can you see that most some don't even get to 90%? So we can now check what this person has done. So if that person is good, you can just check what he has. This is great. So let me see some other ones he has done. So if you want to learn, right? So this is what I just normally do. If I check the particular one I'm interested in, I'll just look at his own code. Some things will not even make sense to me. Do you get? I'll just say, please, I've not gotten to this stage, right? But does it mean that if I go through, at least I'll see one or two that are interesting where he has either pick his data, clean his data, done his EDA, look for the kind of algorithm he has done. You get? Those are now things you start looking out for. Okay? Because no two person will do it the same way. No two person will do it the same way. Okay? Ahead, can you see Scalar? Can you see what they have done? This is the scaling I'm talking about. Can you see Scalar? So what it does for you now is that it helps you to what? Scale down. You know, especially when you are working with some data. For example, imagine GDP. GDP is in billions. Growth rate is in percentage, isn't it? Are they the same units?
No.
So what they do is they what? They transform it. They call it scalar. They scale it them to the same level. So that's what scaling does. So you see when they say scalar dot fit transform train, scalar dot transform test. Can you see that? So what are they doing there? They are just what? Scaling. So that's what the scaling is about. Okay. So I'm sure that one we may not have seen before. So by the time you go through different people's listings, there are different codes. There are one or two things you are going to be learning from them. Okay. So all we have done so far is just to be learning what some of the basics. Some of what the basics. Okay. And all these ones, I'm looking for one that who has, and that's how you check which one you can learn from. It's not everybody you can learn from. Because some the way they present their own is so technical that it will not even make any meaning. Let's see which other one again. Okay, let me just, you can just even, let me even type, let's say machine learning. Which one? We have looked at logistics. So let's say logistic regression. Logistic regression. So somebody has used other Titanic regression, isn't it? They use logistic regression. So let's check. Does it have any code here? Beautiful. Can you see what they say workflow? Can you see workflow? Can you see what he's doing there? He's describing what he has done. So he classified, right? Question and problem definition. Okay, so remember, every problem you must put it in what question form, isn't it? What has he done now? First of all, try to classify or categorize them. So that's your variable y, isn't it? You need to understand the class it belongs to. Correlation means you are looking at the relationship between those variables. So all these things you are doing here, you are doing what they call EDA and pre-processing. So when you say you are converting, when you say converting, what does converting mean? When you say you are converting, what does converting mean? When you say
like to make the numbers, make the text into numbers, transforming
exactly.
strings.
So for example, that survive, you know, say survive, not survive, survive, not survive. So I'll convert that survive into 1, not survive into 0. Okay. So by the time you read through what he has done, then you now start understanding it. Beautiful. Can you see what we are saying here? Logistic regression, linear support vector, isn't it? Random forest, KNN, Gaussian, what? Naive Bayes, isn't it? So these are that one, SGDC. I don't know which particular one that one is. Maybe still supports gradient something. But we'll check through what he has done so far. Can you see how they have brought the different machine learning models? All these are under what? All these are under what? Classification.
Classification.
But you don't see that you need to understand what they're actually trying to do there. Now, can you see when they say ensemble? Do you understand the word ensemble now? When you say assembly, what does assembly mean?
So gather.
Yeah, so either you are applying bagging or what boosting. Random forest, which one does it use? Random forest, which one does it use? We mentioned it now. Random forest, which one does it use? It uses the bagging method now, isn't it?
Yes, bagging.
Yeah, because we talk about boosting, isn't it? We're talking about boosting now. Under boosting, we'll talk about what? Gradient boost, extreme gradient boost, adaptive boost. Okay, so all the kind of boost there. Okay. Now I also like this guy's work. Please look for use this guy work. This guy work is also good. At least it's well detailed. At least for beginners, it's well detailed. And that's another thing you must also learn. Remember, I also showed you learn how to document. Documentation is very important because in most organizations, sometimes, right, you may not always be there to be answering every question. So it's good that you document each process for what you have done so far. Okay, so that's what you are doing. Data analysis and wrangling. What is data wrangling? When you hear wrangling, what is wrangling? What is wrangling? When you hear wrangling, what does wrangling mean? Data wrangling. What does wrangling? What does it mean?
Like
when you hear wrangling, data wrangling, what does it mean?
So you know it's English, so I don't know that is the English one or.
And we're talking about data science. When you hear wrangling, data wrangling.
I don't know.
Data wrangling simply means cleaning or transforming your data. So data cleaning is just another simple word, data cleaning. Or they also call it pre-processing. Okay, so that's what data wrangling. So when you hear data wrangling now. Okay, good. So you have seen all the features, isn't it? So which features are categorical? This guy is very good. This guy is very good. It took his time to, if you want to actually learn, this is also very good. There was one we saw that was also very good, isn't it? So I say you should also follow that one. This one is also very good. Also very good. So let's come to where he has his algorithms. Where is out? So all these ones they are doing, they are called what? EDA, exploratory data what analysis and preprocessing. Okay, and preprocessing. This guy is very good. This guy's work is very good, very good, because he documented it very well. Survive, not survive, survive, not survive. Okay. So where's the analysis? It's the regression itself. Then another concept again you will hear is hyperparameter tuning. Have you heard of that before? Hyperparameter tuning. Have you heard of hyperparameter tuning before?
No, sir.
When you say tuning, you say when you are tuning, you know, like radio. You know when you used to use radio, when you have tuning frequencies, isn't it? Sometimes it not be clear. You know, you now have to tune it gradually, it now becomes very clear. So when you say hyperparameter tuning, you see those are your features. Sometimes after you have run the model, it may not be very accurate, isn't it? So what you can now do, they call it what hyperparameter or tuning. So it kind of what clean up the data, either like taking the log, either you are doing what a lag, but what you do is just trying to scale them till now they become what clean. So your model now becomes a little bit better, or if not better than the previous model. So that's what they refer to as what hyperparameter tuning. So sometimes it even gives a better prediction after what tuning. So when I hear we are tuning the model, or we are performing hyperparameter tuning, what they are simply telling you there, they are simply what cleaning it further to make it better. So all this one, he's still doing conversion. So this is where his model now starts. Can you see that? This is where his model now starts. Okay. So I'm sure this one will understand what it means, isn't it? Logistic regression, you understand when it's used. Do you understand when it's used? Do you understand when logistic regression is used? Hello.
Yes, we do, sir.
You do, isn't it?
Yes, sir.
Good. So his own accuracy for logistic regression is 80%, isn't it? Then he used another method again. Can you see SVM, support vector machines? Do you understand what is working behind it now?
Yes, sir.
Good. Because most times now I say you may just see them, but you won't understand how you're working at the back end. That's the essence of why I went through the theory for you. Because I may just come and run it for you. I'll just see I have done prediction, but you won't understand what is working. This one is what? 83%. Can you see that? This is what? 83%. See another one, KNN. KNN. Can you see KNN now? See how they run KNN. Do you understand n equal to 3 now? Do you understand this one now? KNN equal to n neighbors equal to 3. N means nearest neighbor. My 3 nearest neighbor. My 5 nearest neighbor. My 7 nearest neighbor. My 9 nearest neighbor. Remember, we say use odd numbers. Can you see the prediction? 84.7. Let's check on that one. Naive Bayes. Can you see naive Bayes now? Can you see naive Bayes? 72. So now, when you see this algorithm, do you understand what is happening at the back end now? Is it clearer what's happening at the back end?
Yes, sir, it is.
Is it clearer now? So this is another one. Perceptions. But this one again, this one can also be part of a neural network. Okay. But what they are using this one, but when we get to neural network, we'll still talk about these perceptrons, ANN and other ones. Okay. But this is strictly for what? Binary classifiers. That's what they are using this one. So this and that algorithm you can use. Okay. Then let's check. That is 78. This other one was which one now? This is so maybe this support vector classifier also. This is 79. Gradients. So let's check another one. Again, this one was having 78. So of all of them now, which is now the best? Decision tree. Hey, look at decision tree. Decision tree 86. Which other one? Random forest. So do you understand the difference between random forest and decision tree now, right? But you see, they are even almost the same thing, because if you don't add more trees to it and you are using the same tree to run the random forest, it will give you the same result. Okay. So based on the evaluation, which one is not the best? Based on the evaluation, which one is not the best?
Random forest and decision tree.
Random. So do you understand why random forest is actually the best?
Because it took
Do you
more
understand why
variation.
random forest is the best? Why?
It took more trees.
Exactly,
decision tree is
because
just
of
one tree.
that assembly method. Isn't it? Because of the word assembly word method. So if you take from this model, learn from it, take his own part. Take from that model, learn, take his own part. Take from his own, learn from his own part. At the end of the day, it's taking everybody's own to build its own. Does this make sense now? You see that to run it is not the problem. But it's to understand what is happening at the back end. That is what the problem is, isn't it? So based on this, that takes what? Because if I was to take between random forest and decision tree, you rather take what? Random forest. Can you see that? So that is how, that's mostly about what? Machine learning. And everything we have done so far is about what? Supervised. Can you see that? But actually, in practice, most time it's under supervised learning you are going to be seeing. Hardly will you see, let me say unsupervised learning. You see some, but most of the problems you may see may actually be what? Supervised learning problems. Okay, so since unsupervised learning cheat sheet. I also told you about cheat sheet, isn't it? It's just a summary of everything that you have done, just in one page. The cheat sheet. Can you see that? So under your unsupervised learning, although we'll come back for this one, but this one is under clustering. So there's another one called K-means clustering. Sometimes you may confuse it with KNN. But this is what? Do you know the difference between supervised learning and unsupervised learning? What is the difference between supervised learning and unsupervised learning? Yes?
I think it's supervised learning. The computer, you're the one giving the computer the data, and it's learning as you give it. But in unsupervised, the computer is like learning on its own from data that it finds, that it feeds, that is fed it like automatically.
Yeah. Okay. Okay. To some extent, yes. Can you see what I'm writing here?
Yes.
Can you see what I'm writing?
We can see your screen, but we can't see what you're writing.
Am I writing something here?
Yes, with red mark.
With
Okay,
red
yes,
mark,
yes.
exactly. So remember that under machine learning, isn't it? We have two parts. Supervised machine learning, isn't it? And unsupervised machine learning. What makes this supervised is that, remember our model, y as a function of x. These are our features, these are our y. For supervised learning, we give value to this y. Is it not? We say it's either 1 or 0. 1, 2, 3. Whether it has order or not order. Or it can take a random number, 1, 1.8, 4, 4.8, isn't it? So this y is usually what? Labeled. Can you see that? So we are trying to use this to predict. But unsupervised, it does not work. There's nothing like y there. It only works with what? Your features. Can you see that? It only works with what? Features. So that is why for a particular feature, if you try to what? Cluster them, that is what? K-means. That's one of the methodology called K-means. If you try to what cluster the variable based on the features. Say this guy, you guys remain the same, you guys look similar. This guy, you guys look similar, you guys look similar. It is almost like that KNN, but KNN is usually for the target variable. This K clustering is for what? The features. So there you can now talk about what? Hierarchical what? Clustering. So that's the basic difference between your unsupervised and supervised. So for your supervised, you usually have your Y, your target variable. But for your unsupervised, you don't have like your Y. You only have just the features. So that's why you can talk about what? K clustering. You can also talk about, there's another one called PCA, principal component analysis. There's another one called dimensionality reduction. Dimensionality reduction. I don't know if they have it here, but those are your typical unsupervised learning algorithms. So see principal component analysis here. Can you see it here? That is it there. But sometimes the way they do it is, the way they write it is so technical that you'll be wondering, hey, will I ever understand this thing? But just understand what is used for in general. Don't mind all this, they are plenty grammar. Okay, so that's just the basic difference between them. So when you are learning them, you just, so for now, just focus on what? The supervised learning part. Okay, focus on supervised learning, because to get to a point, we will still come back to this unsupervised and look for how to run the algorithms. But if you can learn that on your own, that's also fine. Okay, but basically that's how you are going to be learning most of them. So if there's any other one you want to learn, for example, they say EDA, Champions League. What is EDA? What is EDA? What is EDA?
Exploratory data analysis.
Exploratory data means that you don't use any machine learning, isn't it? It was just what? Exploratory data what analysis, which means they're only using visuals to just explain it. See, that's descriptive of visuals, or use your, what they call it now, or use your pivot tables and present them in tables. That's just basically what they are talking about there. So the graph, can you see the graph? Now, don't forget, anytime you are working with this, make sure you put the numbers there so that you can actually see what's happening. So right, can you see that now? Who scored more? Right-handed or left-handed people? Can you see that? So more right-footed header and others. Graph 2, number of fouls by teams. Can you see that? Just pick a particular project that you're interested in. I'm sure this guy is passionate about football, isn't it? You pick the data and just exploring the data. That's all. EDA. So all these are called what? Exploratory what? Data analysis. Whose role is it to be doing this EDA like this? Whose role?
The analyst.
Data analyst, exactly. Data analyst. But when you are building machine learning model, whose role is that?
I think that's the scientist.
That's the data scientist. Can you see that? Now that machine learning model, when they want to now implement it live, whose role is that?
So what do you say when they want to
implement that machine learning model that data scientists have built? Whose role is that in terms of deploying it?
Like the engineer?
That is machine learning engineer, correct? Machine learning engineer. Then the one that will check the whole pipeline to ensure that everything works end to end. Whose role is that? That is now called the analytics engineer. Can you see how the roles has gradually changed? Before, you call everybody data scientist or data analyst, but gradually they start separating them. So those who are now specialized in different areas, they now give you those roles. Are those roles now clearer now?
Yes, sir.
So which one do you want to play now? Which one do you want to now play in? That you are a data analyst does not mean that you will not learn Python R. And take note, when we get to R, you see that R, as long as you understand how to do it in Python, you just understand the syntax that you are going to use for R. That's all. But it's the same thing you are going to be getting, the same result, the same everything. It's just with a different language. That's all. Okay. So by the time you come to your cargo, look for competitions, try different, look for different people's algorithms and see how, especially this particular guy and that other one I showed you, because these guys are quite good. Let's say KNN. Let's see KNN. So for example, if you're asking which data set can I use for KNN, you now check what data set they have used and try and build on it. Even like this KNN, they may also have their own charts too. They may also have their own charts. Let's check. Let's check. So this is 1 and 0 now, isn't it? So this is the variable they want to use. I'm sure this one, we know how to do all these ones now, isn't it? Pair plots. Which map, which chart is this? Which chart is this? Which chart is this? Which chart is this one? Yes, that is heat map now.
Heat map.
Heat map. It's just plotting your correlation now. That's heat map now. So Y scaling, can you see that Y scaling? Can you see this distance ahead? Look at this. Can you see Euclidean distance? Does this make sense to you now? Euclidean distance. Do you understand this now? It is the method of just calculating the distance between what those your groups. So can you see that with this cargo, you see how you can learn with cargo? Once you have learned the basics, so keep improving yourself. Just go through everybody's cargo of what they have done and start trying to study it, what they have done and how they did it. Can you see the charts now? Can you see the charts of how they have plotted it? So any new data set now, you either be calculating it, either it's going to be on this side or on this side. Confusion matrix. I'm sure we don't have to interpret confusion matrix now.
Yes.
So you see everything that you have seen here now. Can you see that we have covered almost everything in terms of supervised machine learning? Remember I mentioned something called hyperparameter tuning, isn't it? Hyperparameter tuning. Do you remember that?
Yes, sir.
This is exactly what it is. This is it here. This is how to implement it. Hyperparameter tuning. So can you see that now? What was the previous the guy's previous this thing before? His accuracy score was what? About 77, right? After hyperparameter tuning, it's still almost basically the same thing. It's still almost the same thing. So this is the hyperparameter tuning. This is how to perform hyperparameter tuning. So just for you to take their code and what go with it, just understand what it is. Okay. So as you keep practicing, it will get clearer with it, because everything, remember I told you that the code is not the problem. Can you see that the code is not the problem? The problem is what? Understanding what they are doing. Okay. So if you just, so each of those algorithms we have done, just search for them, then go one by one and just be checking what everybody is doing, isn't it? Try the different data sets. Then gradually you now start seeing that, okay, this is what they have done. And while you are going through it, you'll be understanding how they are either cleaning their data, how they are transforming their data, how they are doing their visualizations, isn't it? And ultimately how they are doing what? Their predictions. So you see, everything that we have done here is the same thing that they are doing. Everything we have done. Okay. So rebuild it. Can you see before they had used K of 3, isn't it? Now they are using K of 5. Can you see that now? Do you understand what this means now? So rebuild it. They used scale of 3 before. The model did not perform so well. So now they want to use scale of 5 to try now. Now, can you see the model now? Can you see the model now? 0.97. Now they are trying again, K of 6. But most time is preferable. Use what? Odd numbers. Use odd numbers. Use odd numbers. Use odd numbers. So that you don't go and start having like a tie. Before you say doesn't know which one to take, whether it's this or this. So to choose one for you. Okay. So that's just basically about machine learning. I think with this, we can end machine learning for this month and everything about Python for now. Is that not? So subsequently, for next month now, for the month of August, now what are we going into now?
From our previous conversations, the options that we were talking about were either Power BI, R, or Tableau.
So which one do you want now?
Should we put it as a conversation on the group, or can you guys just score us what you want now?
Anyway, because since most of us are attending, these are the people that are here, right?
Yeah,
So
true.
let's agree.
Power BI for me.
Power BI for me too.
Power BI for me, please.
Okay.
Yes, another person to Power BI, right?
Yes, Power BI, I agree.
Okay. So Power BI, okay? So that means from next week, so by this week, we should all try and install Power BI. Is that okay? Try and install Power BI by this week. Please take note, Power BI is only for those that who are using Microsoft. If you are using Apple, you're on your own. So please just try and get a Microsoft Windows laptop to make life easy for you. It's not that you cannot do it on, but it's going to be a bit technical a bit. But you have to go and install Windows. Inside the Windows, install Power BI, and before you can run it on Mac. Okay, so this week we'll try and install Power BI. Okay, but please make sure this Python you keep practicing it, because I can guarantee you the moment you leave it, it's going to leave you. Okay, so keep trying different projects, and as you try many of these projects, you'll be putting them in your portfolio, your project portfolio. Excel, you should have some. SQL, we have done SQL now, isn't it?
Yes, sir.
Yes.
You should have 1 or 2 projects on SQL. Python, you should have like 3 or 4 projects in Python. One with basic EDA, exploring data analysis, and just be 2. You can have machine learning, at least do some for regression, do one for KNN. Just use each algorithm. Make sure you have one project for each algorithm like that. Okay, so you see your project portfolio will keep increasing. Then by the time we get to Power BI, we'll do another 2 or 3 projects. By the time we use Tableau, 2 or 3 projects. What are we now showing? By the time you put all of them together, you are showing what versatility, your what skill sets and the tool sets. Is that okay?
Yes, sir.
All right, ladies and gentlemen, we are playing now. So
thank you,
enjoy
sir.
the rest of your weekend.
Thank you, Dr. Francis.
Thank you, sir.
Remember to always practice. So, so by the way, IJ, please make sure when you compile them, make sure you have all the videos. Excel, SQL, Python, isn't it?
Okay.
Then inside Python, specify which one is machine learning.
Are you talking about the videos?
Yes, the videos, yes.
Okay, okay.
When you get to Python part, anyone that is machine learning, put it in brackets. Python, open bracket, ML, machine learning.
Okay.
Yeah.
Okay, no one, sir.
Because much later now, it will be difficult for us to separate which is which.
Yeah.
All right, take care.
All right.
Bye bye, sir.
Bye bye.